Conservation in collisions.
Alright, today I want to highlight two key physics concepts. The first being momentum. So, momentum is a fundamental quantity in physics that essentially describes how hard it is to stop a moving object. So, momentum is a vector quantity. This means that momentum has both magnitude and a direction. Momentum is represented through the equation P equals mv, where P is your momentum, m is your mass, and v is your velocity. The key thing we want to highlight is momentum is conserved, and we know this through Newton's third law. Newton's third law states that for every action there is an equal and opposite reaction. So this means that forces always occur in pairs. So for example, if object A exerts a force on object B, according to Newton's third law, we know that object B will exert an equal and opposite force on object A. So this is how we know and arrive to the conclusion that P1 equals P2. Thus, momentum is conserved. The second concept we want to highlight is kinetic energy. Kinetic energy is represented through the equation K equals 1/2 times m times v squared. Kinetic energy is simply the energy that an object has because it is in motion. In kinetic energy, you have two fundamental concepts, elastic and inelastic collision. Today, the lab will look at both sides of the spectrum. So here in activity 1, we essentially replicate what an elastic collision would look like. The key thing we want to highlight from this activity is that momentum is conserved as well as your kinetic energy. In the lab, we stimulate this collision through a magnet-magnet collision. So what will happen is a moving cart will collide with a stationary cart. This will replicate an elastic collision because the magnets will repel without touching. This allows for there to be no reducing deformation and energy loss, thus conserving energy, making it an elastic collision. So let's take a look at that video. Activity 2 takes a different approach on the same concept. The key difference between the two activities is that in activity 2, both carts are going to be moving, thus both having momentum. They collide with each other, but when they collide, they still collide through a magnet-magnet collision, thus replicating a elastic collision, because magnets repel without touching. This allows there to be no energy loss, so both activities follow kinetic energy being conserved as well as your momentum. Let's take a look at the video and see it for ourselves.
In trial 3, cart 1 begins at rest while cart 2, which carries a 0.5 kilogram weight, moves toward it. When the two carts collide, the Velcro causes them to stick together and move together, mimicking a completely inelastic collision. Because the carts lock together, the kinetic energy is not conserved. However, the total momentum of the system is conserved. Before the collision, only cart 2 has kinetic energy and momentum because cart 1 is stationary. After the collision, both carts move together with a shared velocity. Due to Newton's third law, the system experiences equal and opposite internal forces during the collision, which means that P initial is equal to P final. Kinetic energy is not conserved because some kinetic energy is transformed into deformation energy, sound, heat, vibrations, and other factors. The equation P initial equals m1 v1 plus m2 v2 simplifies to P initial equals m2 v2 because cart 1 has no mass or velocity. Then the equation P final equals V final times m1 plus m2 represents the momentum after the collision. If we set these two equations equal to one another, we get m2 v2 is equal to velocity final times m1 plus m2. We can solve this equation to solve for the final velocity. We get an equation of velocity final is equal to m2 over m1 plus m2 times v2, which is shown on the slide. This equation correctly illustrates that because cart 2 is 0.5 kilograms heavier, the shared velocity final of the system will decrease.
The top row of graphs show the momentum of each cart over time in activity 1 on the left and 2 on the right, displaying the transfer of momentum from one cart to the other in elastic collisions. We can see that the absolute value of the minima on the graph have the same value, which indicates that momentum is conserved. The bottom row of graphs show the kinetic energy of each cart over time. These graphs also show that all the kinetic energy was transferred from one cart to the other in the elastic collisions due to the maxima having the same value, demonstrating conservation of kinetic energy. This graph shows the momentum of each cart in the inelastic collision. We will use the absolute values of momentum to interpret our results. Since the values of the lowest points are the same, we can see that all the momentum was transferred from one cart to the other and is conserved. In inelastic collisions, kinetic energy is not conserved. The graph comparing the kinetic energies of the two carts over time shows a steep drop just after the collision, indicating that kinetic energy was lost as the carts decelerate after the collision, and it is not conserved.
In this lab, we compared elastic and inelastic collision scenarios by analyzing graphs of momentum and kinetic energy before and after collisions. From these graphs, we calculated the system's total momentum and kinetic energy before and after each collision. If either quantity is conserved, the expected change is zero, so the absolute error equals the average difference in momentum and kinetic energy. In activity 1, where cart 1 was initially at rest and cart 2 was moving, the average difference in momentum was 0.008 kilogram meters per second, and the average difference in kinetic energy was about 0.002 joules. As you can see, our standard deviation and standard error values for this activity are very small, demonstrating the consistency between trials and reliability of our results. In activity 2, where both carts were moving toward each other, the average difference in momentum was 0.018 kilogram meters per second, and the average difference in kinetic energy was about 0.003 joules. Our standard deviation and standard error values are very small for this activity as well, demonstrating the consistency between trials and reliability of our results. Both activities demonstrate that momentum is conserved in elastic collisions with reasonable experimental uncertainty, which is expected for all real-world collisions due to frictions and transformation of small amounts of energy. Although activity 2 displayed somewhat larger differences of greater error, our results are still reasonable. Additionally, because these are elastic collisions, kinetic energy should also be conserved, and the small differences we observe can be explained by experimental errors such as friction, transformation of small amounts of energy, sensor limitations, and timing inaccuracies. Overall, our results support the theory that elastic collisions conserve both momentum and kinetic energy.
For activity 3, we analyzed an inelastic collision. In inelastic collisions, momentum is conserved, but kinetic energy is not. This is why our absolute error for momentum was very close to zero, being 0.008. In contrast, our absolute error for kinetic energy was much higher, at approximately 0.05, which was higher than in the other activities. This difference is expected for an inelastic collision. Our results also show strong consistency across trials. For momentum, the standard deviation was 0.0041, and the standard error was 0.0017, both of which are very low. For kinetic energy, the standard deviation was 0.0196, and the standard error was 0.0080. These low values indicate that our measurements were consistent and closely grouped. Overall, the low absolute error for momentum and the low standard deviation and standard error support the accuracy and reliability of our results for activity 3.
One of the most important real-world applications of the concept of conservation in collision is during car crashes. When two cars crash into one another, the total momentum of the system must be conserved, meaning that the momentum of the system before the crash is equal to the momentum of the system after the crash, similar to what we did in our experiment. Although cars crumple and deform during crashes, momentum is still conserved. Engineers focus on the same concepts that we explored in this lab, and understanding these concepts of conservation during a collision is crucial to preventing dangerous crashes and potential deaths. This is why cars have crumple zones. These are sections in the front of the car that are designed to crumple in a controlled way during a crash. By allowing certain parts of the car to compress and crumple, the time of collision is extended, which means that the force experienced by the driver and passenger is dramatically reduced due to the impulse momentum theorem. By increasing the duration of the impact, the force applied to the driver and passenger decreases. This feature of the car does not alter or try to change momentum and conservation laws. They simply manage how momentum is transferred to prevent serious injuries and potentially fatal ones as well. The same laws of physics that applied to our experiment when two cars collided applies to real life and is crucial for designers and engineers to understand, and they play a critical role in preventing serious injuries.